We next go to the acceleration. The acceleration is the rate of change of velocity. Okay. Acceleration is the rate of change of the velocity rate of change of the velocity. For a finite time interval, we will define the average acceleration as follows. The average acceleration AX AVG is equal to the delta Vx over delta T. Okay, so it's the average rate of change of the velocity. Average rate of change of the velocity. We can see that since Vx is a vector, so the average acceleration is a vector also. And for one-dimensional case, we use the sign of AX of the average acceleration as a direction. As the direction of the average acceleration. So we will have that the average acceleration can be positive or negative. We can have both positive average acceleration or negative average acceleration. Like for the velocity, we will also define the instantaneous acceleration. The instantaneous acceleration. Using the concept of calculus, we will write the instantaneous acceleration as the limit of delta t approaching 0 of delta Vx over delta t. Or using the calculus notation, it is the dVx by dt. We can represent the acceleration graphically also, as in the case of the velocity. In this figure, the graph on the right represents the velocity of the car moving from point A to point B. If the car moves with the acceleration, the velocity change in time as you can see in this graph. Okay, and if you want to calculate the average acceleration in the time interval Ti to Tf, it is the slope of the line joining point A and B, this line, and the slope is the average. The slope is the average acceleration between the time interval delta t, which is equal to the Tf minus Ti. If you want to calculate the instantaneous acceleration, or as in the case of velocity, we will call it just the acceleration. The instantaneous acceleration, or the acceleration at B, is the slope of the tangent line at point B. The slope of the tangent line at point B in the VT diagram. It is useful to be familiar with the relation between VT diagram and AT diagram. In this figure, the both diagram is a VT diagram, and at the bottom is an AT diagram. You can see that at point A, at time Ta, Ax reach the maximum value. So it means that it on the left of Ax increase, on the right of Ax decrease. So if we look at the slope of Vx before the point A, the slope is increasing, but on the right of point A, the slope is decreasing. So the change of the slope here represents the change of the value of Ax here. At point B, we can see that the acceleration is 0. So it means the slope of the VT diagram here at point B is 0 to 2. Okay. And you can see that on the left of the point of the time Tb, before the time Tb, on the left of the point B, the acceleration is positive. So it means that the slope of the VT diagram is positive. Also, you can see that the slope on this part of the curve is all positive. But after the time Tb, you can see that the acceleration becomes negative at this part. So the slope of the VT diagram is negative on this part too. And finally, at time Tc, you can see that at the time Tc, the acceleration reached its minimum value. So when we look at the slope of the VT diagram, the slope change from decreasing. You can see that in this part the acceleration decreased. Okay, but after Tc it increased. So the slope of the VT diagram here decreased and then it decreased. But in this case, you can see that the slope is negative. So decreasing means that it's more negative, and increasing here means that it's less negative. Okay, so this is the relation between VT diagram and AT diagram, and you should be familiar with this.